All right, hello again, and welcome to the final lecture of this day. So I'll tell you about. So you shouldn't expect any theory in this talk. So this talk is about a bunch of cool empirical results, which we do not fully understand yet. But it would be cool if someone comes up with some convincing explanations. So in this talk, I will tell you about variance networks and works on investigating the loss of faces. So let's return to the variational dropout model. So we have this Gaussian dropout. Everything is just as before, but now we only have one alpha per layer. So we have this multiplicative noise over the weights. And the scalar parameter alpha is now common for all the weights inside each layer. So let me remind you of the variational dropout model. So we have the common evidence lower bound. We have now this posterior approximation, which is basically Gaussian dropout with just one alpha per layer. And we have the same prior distribution as before, which is the log from prior. So in sparse variational dropout, we switch from this distribution from this parameterization to additive parameterization and obtain a sparse solution. But if we try to optimize the variational lower bound like this, in this original parameterization from the Kingdom's paper, well, something weird would happen. But first, let me tell you about several different prediction schemes. So in stochastic neural networks, you can come up with basically three prediction schemes. One is ensembling, the other one is stochastic prediction, and the third one is deterministic prediction, or the Bayes scaling rule. So in the ensemble, you sample the weights from your approximate posterior distribution, and you average the network outputs across different weight samples. So you take k samples, like maybe 20 samples, and then average the softmax outputs. In stochastic approximation, you only use one sample. So this is very similar. And in deterministic, instead of sampling, you use just the expected value and discard the noise. So this is this weight scaling rule heuristic. So for example, in dropout, instead of using the random dropout masks, you use the dropout probability instead. So in case of variational dropout, you just use the expected value of the weights to make prediction, just as you did in the seminar. So what happens when we try to fit the variational dropout model? So we have this, we track these three possible prediction methods. So deterministic, stochastic, and assembling during the training. And yeah, this is measured on the test set. And you can see that all of them behave, well, practically the same. But after some epoch, ensembling and stochastic continue learning just as well. But deterministic prediction goes to a random guess quality prediction. So something very weird happens. So it turns out that around epoch 50, the alpha, which is 1 for a single layer, goes to infinitely large values, like 10 to the power of 5. And the network goes to a very strange regime. So in sparse variational dropout, if all alphas for a single layer would go to such values, you would just sparsify the layer completely so that all the weights and all the variances will essentially be 0. But here, this is obviously not the case, because if you set all the weights to 0, you cannot propagate any information through this layer. You would obtain a random guess quality even if you perform stochastic or ensembling prediction. So here, it turns out that the weights go to 0, but the variances do not. So let's take a look at how the alpha is computed. So alpha can be computed as the fraction of the variance over the mean value squared. So 1 over alpha is actually called the signal-to-noise ratio, or like the expected value squared over the variance squared. And it is very, very low, like 10 to minus 5. It means that the signal-to-noise ratio for this particular layer is 0, essentially. And the means are negligible compared to variances. So what you can do, and you can actually show it, is that you can take this approximate posterior distribution with mean W and variance alpha W squared, and actually substitute it with a zero mean distribution. So this is a Gaussian distribution with zero mean and some variance sigma squared, which are equal to alpha mu squared. And you can actually show that as alpha goes to infinity, the maximum mean discrepancy between these two distributions goes to 0. And that means, so basically what maximum mean discrepancy means is that no function, no discriminator can distinguish between those two distributions. So if you plug these distributions inside your neural network, well, the neural network, the output would be exactly the same. So, and this is what happens here. We can substitute this learned approximate posterior with this zero mean posterior, and the predictions would not change. So this is called variance networks, because like there is a layer which does not contain any means. All the means are 0, but there are some non-zero variances. And you can see it as a special case of Bayesian neural network trained with variational inference with a very strange kind of approximate posterior distribution, where the approximate posterior is actually a zero-centered Gaussian. And it turns out that if you consider this zero-centered Gaussian and the same log uniform prior as before, the KL divergence term, which was before a function of alpha, now remains constant, because like the alpha is always infinity and it does not depend on sigma anymore. Like if sigma is 1, if sigma is 10, alpha is always infinity, so the KL divergence term remains constant. So basically what you have here, you just have this data term, and you have no regularization on variational parameter sigma. And you can discard this KL divergence. So it turns out that it works surprisingly well for classification, and it actually provides even better evidence lower bound than sparse variational dropout does. So here what we do is we consider several different parameterizations of variational dropout model. So here is this layer-wise parameterization, neuron-wise, weight-wise, and additive. So additive parameterization is equivalent to the weight-wise parameterization, but as you have seen in the first lecture, the gradient variance for the additive parameterization is much better than for the weight-wise. And layer-wise and neuron-wise parameterizations are special cases of weight-wise and additive parameterizations. And they are much less flexible, so you cannot cover all possible fully factorized Gaussian distributions using just these parameterizations, because you have less parameters. But still, you obtain much better values of alpha. So, for example, like for the additive parameterization, you have this -2 times 10 to the 4th, and for the layer-wise, you have -7 to 10 to the 2. So it is like 2 orders of magnitude better. So what actually happens here is that the data term remains the same across all different parameterizations. So the network is still able to learn very well. But the KL term for the layer-wise parameterization goes to 0, essentially, and the same for the neuron-wise parameterization. But for the weight-wise parameterization and for the additive parameterization, well, it gets stuck at some pretty high value. Yeah, so it turns out that you can just take a less flexible posterior approximation and obtain a better approximation to the posterior distribution, which is quite surprising. So the main idea and the main intuition for why this is the case is that if you have a lot of different parameters, like here, both the mean and the variance are trainable, we introduce a whole bunch of local optima, which are suboptimal in terms of elbow. So when you try to learn the sparse variational dropout model, you actually get stuck in these local optima, in these suboptimal solutions. And it happens so that these poor local optima are actually quite useful. They correspond to sparse solutions. But if you would try to optimize the evidence law about rigorously to strike for the best possible value of the objective, well, then you would not obtain such sparse solution, and you would converge to variance networks, which is a very strange regime for a neural network to be in. And so here are some classification results. So as you can see, this variance network performs very similarly to a conventional dropout network, and we were able to scale it up to VGG-like network on CFR 100 and obtain quite good accuracy there. And so we could not obtain the fully variance network where each single layer is variance, mostly due to the fact that they are still pretty hard to train. The variance of the gradients is quite high, but we were able to train a VGG-like network with 6 consecutive layers being fully variance. And so, as you can see, you have this huge gap between the stochastic prediction and the ensembling, from 96 to 99, from 77 to 82. So this gap is much less for example, for dropout. And as for deterministic prediction, well, of course, for variance networks, it does not work because you just substitute all your weights with 0 values. And you obtain pretty much a random guess quality prediction. Yeah. And also what the discrepancy between this stochastic accuracy and ensembling accuracy tells us is that we actually have very much diversity between the networks. So we were able to pack a whole lot of different models inside one stochastic computational graph. So how can this actually work? It seems very strange. The signal-to-noise ratio for each layer is 0. How can it propagate any information? So for this, let us consider a simple toy problem. So here is a 2-dimensional data set, a classification problem with 4 classes. And a very simple neural network with several fully connected embedding layers, and this one variance layer with 2-dimensional output, so that we could plot the activations of the variance layer. And we have this predictive layer, which is basically just one layer that has softmax output after it, and it classifies between the 4 classes. So if we train this network to convergence and look at the activations of the variance layer, we can actually see how the network classifies the classes. So even though for every single object, for every single class, the average activation is equal to 0, they all are centered at 0, the variances are very different. And this is one example where different classes go to these different energy levels, and you can easily see that if you are over here, this is probably the yellow class. If you're here, this is the green class. Here, this is the blue class, and here, this is the red class. And this information is enough for quite robust classification. There can be also another scenario where so here, all the variances are the same. All the variances for 2 neurons duplicate each other, and here they're different. So for the yellow class, both variances are large, for example, and for the green class, one variance is high and one variance is low. So if you are near this axis, you have the green class. If you are near this axis, you are near the blue class. And you can take the activations for neural network and plot them, well, basically the same way. So you can take a neuron, single neuron, and plot the activations for different classes. And you can see that for different classes, you obtain significantly different variances. And of course, if your layer is pretty high dimensional, like 300 neurons, 500 neurons, you can easily distinguish between these large variances. And here you can also see another training curve. So you still have this blue line of deterministic prediction. You have this orange line. Well, you actually can't see it there very well, but it's just like on the top here of the ensembling prediction. You have this green line, which is the variance prediction, where during prediction you zero out the means and only use the variances to predict. And as you can see, in the beginning, the variance prediction is random guess quality, and in the end, the variance prediction coincides with the ensembling prediction. And you can take this permuted prediction, where you permute the variances inside the layer so that you try to remove all the information from the variances, but still obtain some stochasticity. Yeah, and so in this plot, you can see how the information actually flows from the means to the variances. So in the first 20 epochs, you can fully rely on your mean to predict, to obtain high quality predictions. But then, as soon as the variance prediction starts to grow, the deterministic prediction starts to go lower, and you can only use one of them to perform good predictions. In some cases, usually this blue line drops right before the green line goes to the full capacity, but in some cases, you can obtain these interesting points, like here at epoch 32, where the network can actually predict in both prediction schemes, both deterministic and variance. So it seems like both of these regimes convey basically the same information, but in different ways. All right, so do you have any questions regarding to variance networks? Yes. Slide 13. Yes, so basically these are two separate networks trained from two different initializations. So sometimes you obtain this solution, sometimes you obtain this solution. Yeah, so there are several ways to encode this. Like here, it is like binary encoding. Either the variance is low, either it is high. And well, for the yellow class, both are high. For blue and green, one is high, one is low. And for the red one, both are low. And here, the encoding is not binary, but the information is shared between these two neurons. Yes?
So if the Kyle term is constant, does it mean we cannot really overfit on this model?
Well, it depends on how you define overfitting. So this model is quite difficult to train, right? So it is difficult to overfit, more difficult because it is difficult to fit. Yeah, you can't overfit if you underfit. Yeah, but essentially, no, because you still have this stochastic computational graph with sigmas that you try to fit, and you have no regularizations for these sigmas. So yeah, in theory, you could overfit. If you obtain a better training procedure, which can reduce the variance of the stochastic gradient, and well, we're actually trying it right now. We want to try to train these networks using the recently proposed deterministic variational inference. Maybe someone heard about it. There's a paper from the last SLR. Yeah, but in theory, yes, it can be overfit. Okay, so this is a very strange model. So this is an example where this weight scaling rule, which is extremely common in deep learning, can catastrophically fail. So this weight scaling rule basically usually applies to most stochastic computation graphs that you see. For example, if you use dropout, you use weight scaling rule. If you use batch normalization, it is also a stochastic computation graph because you can, for each object, you can pick different objects to the mini-batch, and the mini-batch statistics would drift. And during predictions, you use these average statistics that you calculate using moving averages. So this rule is very common. people usually use it blindly and do not care whether it works or not. So a good idea would be to use both the Bayes scaling rule and stochastic or ensembling prediction, and then see whether the Bayes scaling rule provides you with some terrible accuracy degradation or not. If it works well, okay, good for you. If it does not, well, it doesn't mean that the model is bad. It means that you are not doing the predictions correctly. And in order to predict from this model efficiently, you need to either use distillation or use some other kinds of deterministic propagation techniques which are more accurate than Bayes scaling rule. Okay, so if you obtain the random guess quality at test time, it does not mean that the model is bad. It just may mean that you are not doing it correctly. So I hypothesize, so I don't know for sure, but I think when Kingma first proposed this variational dropout model, he had to clip the variance, the alpha values to low values from like 0 to 1 because of this problem. Like he saw this accuracy degradation and said, well, maybe this variational dropout is not so good. I will just try to clip the alphas. But it turns out that large alphas can be quite interesting. Also, another very interesting result is that more flexible posterior approximation does not mean higher elbow. So usually, in order to obtain like a better evidence lower bound or better test time likelihood, you try to come up with more and more flexible posterior approximation. Like in variational autoencoders, you stack a whole bunch of super complex normalizing flows or something like that. You introduce a whole bunch of new parameters, and well, it does not mean that the model gets necessarily better. Sometimes it becomes worse. And the final funny thing is that it seems that modern neural networks can withstand just absurd amounts of noise. Like you can take a neural network and train it in such a way that each weight is like completely random. Yes, different weights have different variances, but each weight has a completely random sign, for example. And this is a little bit mind-boggling. Okay, so let's continue to the investigation of the loss surface. And this is a pretty long line of works from our group and from our colleagues at Cornell University. So let's consider, so there is basically no Bayesian stuff here. You can relax. There will be no complex math or anything, just a bunch of cool empirical results. So consider a typical neural network. This is like a huge complex function of millions, hundreds of millions of parameters. And you want to imagine its loss surface. So everyone knows that the loss surface of deep neural networks is a highly non-convex function. And it has a huge amount of local optima. And yeah, so for example, it can grow exponentially. So you can permute the neurons and obtain like the same function. So that means that the optimum is still basically the same, but the weights are actually different because you have permuted the rows of the matrices. Okay, so if you would like to imagine a typical loss function, basically, usually something what comes to mind is something like this. So you have these several local optima, which like these disjoint Gaussian-like things. And if you try, so indeed, if you try to take like 3 random optima, and you try to cut the loss surface with a plane that goes through these 3 points, you would obtain something like this. So this is a real picture for ResNet 164 and CFA100. And you can see these 3 smooth Gaussian-like local optima. However, it turns out that this is not the correct intuition. The loss of a neural network is not a set of disconnected local optima. It turns out that you can take any pair of local optima, and you can connect them using a very simple path, like this Y curve here, or this polychain with just 2 segments. And the training loss across these curves would be exactly the same, right? Yeah. Yeah, so you have like this figure here. So you have 3 points, like W1, W2, W3, right? And then you take 2 vectors, like W1 minus W2, or minus W3, and W3 minus W2. Yeah? And you can take these 2 vectors and then use them as your coordinate axis. So you take all possible linear combinations of these 2 vectors, and you obtain a plane. So a plane is defined by 2 vectors that lie in this plane. Yeah, and here, you can, for each point on the plane, you can compute the loss function. And yeah, this is what you see here. And the same thing happens here. So we have these 2 optima, which are the same optima as in the previous slides, but the 3rd point is different. So this is a parametric point, which we are trying to find in such a way that the loss function would be constant along this path. Yeah. And well, we weren't able to find any pair of points that you could not connect. Like for every network, for every problem, any 2 points can be connected. It is very difficult to prove this rigorously, of course, but there have been some works that try to prove it, of course, with some very strict assumptions. But I think it is something that will be proven sooner or later. So yeah, any pair of optima can be connected by a very simple path. And it means that there are actually no local optima in neural networks. There is just a very complex manifold of solutions. So this loss function actually does not look like a set of disjoint local optima. Instead, it looks like some kind of sponge where like each point on the sponge is a local optima, a point with a very low training loss. And all these points are connected. So how this connection procedure works? So you have your loss function, for example, cross entropy loss, and you have these 2 snapshots, W1 and W2, that are already trained and fixed. There's 2 separate local optima. So then you define a parametric curve phi with parameters theta, so a curve is mapping from 0, 1 segment to the weight space of the neural network, such that at this function at 0 coincides with W1, and this function at 1 coincides with W2. And then you have this parametric curve, and you minimize the loss along this curve. So in order to do this, you want to define a uniform distribution along the curve. And basically, the simplest way to do it is to integrate the loss function along the curve phi. So you do it like this. You take an integral from 0 to 1 of your loss function times the norm of the derivative of the function that defines the curve. So this is like basic calculus. And you integrate it, and then you need to normalize this thing because the length of the curve in this T space can be different. So you need to also divide by the length of the curve, which is computed exactly the same way. So you now have this average loss across the curve, which you want to minimize. And of course, you can pose this thing as a distribution over T. So this distribution is defined as follows. Like this is just the norm of the derivative over its integral. So you just need to normalize it. And then you can write this connection procedure as this stochastic optimization procedure where you have your loss function at point phi theta of t, and you sample t from this distribution q of t. And this distribution allows you to obtain distribution over t allows you to obtain a uniform distribution along the curve. Okay, so this is a very simple objective, which is very similar to what you've seen before. So stochastic optimization could be applied. However, the stochastic gradient with respect to theta is in general intractable, so it is not always possible, for example, to normalize this thing. So a simple heuristic can be used where you just use a uniform distribution in the t-space. So in general, for very complex curves, you would need to do something like this, because if in some complex curve parameterizations, a uniform distribution over t would not yield you a uniform distribution over the curve. But for simple curves like Bezier and polychain, a uniform distribution over t is enough, and it approximates the uniform distribution along the curve quite well. So you can use just this. Instead, you sample t from a uniform distribution, you plug it into the curve, and you minimize the loss function. So yeah, this is very simple. And how do you define the curve? Well, there are two simplest examples are polygonal chain and a Bezier curve. So a polygonal chain with two segments is defined as follows. You just have W1 and W2, which are the ends. You have this theta, which has the same number of dimensions as W1 and W2, which is like the third point on the plane. And you connect W1 to theta and then theta to W1 to W2. And in order to do this, you take just convex combinations of W1 and theta and convex combinations of W2 and theta. So when t is from 0 to 0.5, you go to the segment between theta and W1. And when t is from 0.5 to 1, you go to the second segment between W2 and theta. And of course, this can be generalized for more segments as well. And the Bezier curve is a simple quadratic curve, which is defined as follows. So it is easier to implement. Yeah, and we can add more bands to the Bezier curve as well. Okay. So the only thing that is left in order to make this procedure work is to address batch normalization. So you have W1, and W1 has some batch norm statistics, which work well for W1. W2 has another batch norm statistics, which work well for W2. However, for any other point, the batch norm statistics can actually be different. So for every point on the curve, the statistics can differ. And during test time, for any curve for any point on the curve, you would need to compute them separately. So yeah, this for now can't be avoided. So yeah, the only way to do it is just to compute them straightforwardly. And during training, it does not matter because batch norm works in the training phase, where you just take a mini batch statistics, which works the same way for any given weight. And after you apply this procedure, you obtain these pretty pictures. So on the left, you can see the training loss and the test error for the plane that cuts through 3 different local optima. And on the right, you can see the loss along the curve. So on the top, there is the training loss, which is like the same as you've seen before. And on the bottom, which is the test error, which is not constant because we did not optimize for it, but it's still quite low. Yeah, and this behavior is basically the same for all kinds of networks. So yeah, the previous one was ReleaseNet on CFR 100. This is a VGG on CFR 10. Here you have 3 disjoint optima, and here you have these nice paths. There was also another work by Draxler et al., which calls essentially no barriers in neural network energy landscape. And they obtained the same results. So this was a concurrent walk. So they obtained the same independent results. Their connection procedure is more difficult. So they have a polychain with a lot of different points, but they obtain closer fit to the actual loss landscape. So that the training loss remains completely constant. So in case of these polygonal chains, for example, you can see that at this point it goes up a little bit, but yeah, this is just because the curve is so simple. If you make it more complex, adding more parameters, of course, you obtain a much better fit. So they still can be connected. Okay, so what this means for the community. So usually people thought about this local optima as disjoint local optima, but it turns out that every optima has a lot of tunnels that connect it to the neighborhood, to the neighboring local optima. And if you move from one optima to another through the tunnel, you are changing your function quite rapidly. And it turns out that any local optima actually has a lot of different functions in its vicinity. And what actually happens when you try to run SGD with quite small learning rate, so it does not escape one local optima, but you use a cyclic or a constant learning rate that is not decaying to exactly 0, it turns out that plain SGD actually traverses these functions. And it can be quite useful. So you, for example, can take several snapshots during SGD training and then ensemble across the snapshots and obtain a good quality prediction. And this works just as well as snapshot ensembles, which used huge cyclic learning rate schedule in order to escape the local optima. So it turns out that you don't need to escape it because there are a lot of different functions in close vicinity to one optima. Yeah. So if you try to plot several points like W1, W2, W3, which all come from the same local optima, but from different SGD iterations, it turns out that all of them has the same testing error, the same training loss, but the functions are different. So as they're different, you can, of course, ensemble them, and this is called fast geometric ensembling. Or as these weights are actually very close to each other, they come from the same local optima, there are no barriers between these points, you can just average the weights instead as a simple approximation to ensembling. So this is called stochastic weight averaging. This is a super simple procedure that is surprisingly powerful. So the algorithm for SWA is basically the same as the algorithm for SGD. So you just at first warm up your model, like train a neural network to convergence or almost to convergence. And then you perform the same SGD iterates for several more epochs. Like you calculate the learning rate, you do the stochastic gradient update, and then if the time comes, like every epoch, you collect a snapshot. And then you update your running average, SWA, with this new snapshot. So you actually don't need to store all the snapshots, like in snapshot assembly methods. You can just accumulate them and average them instead. So yeah, that is basically all. After training, you need to update the batch norm statistics for this SWA point, because the batch norm statistics, of course, are different for this point. So you run another epoch to collect the batch norm statistics, and that's it. You obtain this SWA point. And you can see the results like on this table. So for huge networks like PyramidNet and ShakeShake, for CIFAR100 and CIFAR10, everywhere you see a huge improvement from SGD to SWA. Like on CIFAR100, it is up to 2%. CIFAR10, it is about 0.5%. And this SWA performs basically just as well as this fast geometric ensembling. So FGE takes the snapshots and averages the predictions. SWA takes the snapshots and averages the weights. And this even scales for ImageNet. So yeah, you can take a pre-trained ImageNet model and then train it for several more epochs and average the snapshots in between. And you obtain up to like 1% improvement, 0.5% on very large networks. So this is something that works out of the box for basically any model. So why does it work? So there is this generally accepted intuition about wide optima and sharp optima. So you can see this training function, which is basically your training loss. And you can see your testing function, which is your testing loss. And your testing function should behave well similarly to your training function, but it can be shifted a bit because the data is different. So when you shift this curve near flat optima, well, the point still coincides with a low value testing loss. But when you shift a sharp minimum, this optima can correspond to a very bad value. And so it is generally accepted intuition that flat optima has much less generalization gap than sharp optima. But this intuition can be misleading. So there is this paper by Dean et al. Where they show that you can actually reparameterize the network in such a way that flat minima become sharp minima and sharp minima become flat minima. And so it is not 100% clear what is going on here, but well, you can still use this intuition as like a simple approximation. Okay, so we can assess the width of the SWA point versus the width of the SGD point. So one simple way to do it is just to connect SGD point and SWA point with a line, with a straight line, and then plot the train loss and the test loss along these lines. And as you can see, this SGD point goes near the edge of the optima. So if you go in this direction, you obtain a very sharp direction, so the loss increases very soon. And for SWA, well, it goes right in the middle of this plateau. So if you go to the left or you go to the right, the loss does not increase very fast. And in this case, it coincides with like, the optima for the testing loss along this curve. Of course, this is just one curve. It is not like the global optima for the test loss. So there is nothing magical here, but still, along some curves, it is a rather good point. And you can take SGD point and SWA point and draw lines in random directions and see how the loss behaves there. And yeah, for SWA, you obtain a wider optima as well, so for any random line. So yeah. So that's basically it about SWA. So I've only told you about the application to classification, but it is actually useful in many other different fields. Like, for example, in generative adversarial networks, you usually use some kind of averaging for your generator so that it stops oscillating around one point. It helps improve stability in reinforcement learning. It helps to provide better consistency in semi-supervised learning. It can be rigged to perform some uncertainty estimation. So in this paper, they take this SWA point and then also construct a Gaussian approximation to the posterior, which is centered at this point. And it can be applied to low precision training. So you can take these low precision points during the training time, average them, and then obtain a high precision point afterwards. So during the training time, you only operate in low precision, which is quite fast. And during testing time, well, you have this high precision network, which performs just as well as the network that was trained in high precision from the beginning. Yeah, so that's basically all. Yeah, there are some links to the related papers. So if you have any questions, you're welcome. Yeah.
Yeah, on the second to last slide where you spoke about this Optima with, no, the one after that. Yeah, so it's on the y-axis there's test error, and so so what's on the x-axis? So I see the test error is going up.
What is the x-axis?
Yeah.
Yeah, so this is basically the distance in the weight space which you follow, like which you go when you follow the line. Like you take this point, take a random direction, and then go like 30 in this direction. So this is the norm of this vector that you add to your weight, to your weights.
Got it. So if you start from a point and then you go farther away, you expect the test error to go higher.
Could you please repeat?
If you take a point on this weight space and then you go farther away from the point, you'd expect the test error to go higher.
Yeah, sure. Okay. Of course, because this point is your trained solution, and if you go far from your trained solution, you eventually obtain a random prediction, basically, yeah. All right, if there are no more questions, thank you all for coming. So this was the last lecture for the school.